Hello, welcome everyone to this video. So let's just recap what we did before. Okay, we talked about the different layers of networking, port numbers and all that. So the easiest way to recap is by looking at our concept of a data packet, right? So the first layer that we need to think of, of course there's the so-called ones and zeros, because electrical signals in voltage signals are being translated to ones and zeros. We call that the physical layer, which you don't really see in here. You don't see so much over here, but you do see the part where we need to talk about MAC addresses, and this is where we talk about the data link layer, and the protocol used is called Ethernet. Okay, so that's where you have all your MAC addresses and everything. Then you're talking about networking, where you talk about internet protocol. That's why we call this protocol IP, internet protocol. So we have internet protocol address or IP address. So that's the networking layer. We covered that already. Then we have the transport layer, which talks about app-to-app communications. But we have not talked about what protocol it uses yet. So there's Ethernet, IP, then what is used for the transport layer. Okay. So based on what we talked so far, transport layer, so far we only discussed multiplexing and demultiplexing. And with all of these features we talk about, the protocol that only cares about multiplexing and demultiplexing and nothing else. Okay, just make sure the data goes to the right application. We call this the usergram data protocol, UDP. Okay, UDP. Okay, is called UDP equals to user datagram protocol. Okay, if you search online, you can look for user datagram protocol. Okay, you just search there, you'll find lots of articles here. Of course, there's a GeeksforGeeks article, and I'll put that in the description. Okay, for UDP, you can see the only things you really care about are the source port and the destination port. Okay, there's also this thing called the length and the checksum. Length actually tells you how long the UDP data is. You don't really need to think so much about that. Checksum is important to do the data integrity check. Right, so let's tie these concepts down with an example. We use the phrase here, the quick brown fox jumps over the lazy dog, and this is a phrase you'll often see in a Microsoft Word or whatever. If you search this thing on Wikipedia, you will see that this sentence actually uses all the letters in the English alphabet from A to Z. Right? So let's say you want to send the quick brown fox jumps over the lazy dog via email. How does it happen conceptually? Okay, step one, you have to break up the message. Okay, because sometimes the message is too big for one single data packet to go all the way through. So what happens is that you have to break up the message. So you maybe break it up into something like that. The quick, then you can have brown fox jumps, and then maybe we'll have them in very similar lengths, right? The quick brown, then we'll have fox jumps over and then we have lazy dog at the end of the day. Okay, you can of course break it up into word by word or even letter by letter. I'm not sure what the data sizes will be. Okay, what happens in the step 2? You remember the socket will assign a port number, source and destination. So right, I will have let's insert a table. We have something like that. So we have 3 separate tables. Okay, so it will be like that. The quick brown will be in this, fox jumps over there will be this, and lazy dog will come out will be this. And I have source port. Let's just call that I'll just give it random numbers, okay? Source port 90 or 48531 dest port what 757, okay? I don't know. Okay, so this is what the part will fill in. Okay, this is the socket will have to give it a port number 3. Socket will encapsulate it. I believe so, I'm not sure. Okay, but anyway, you have IP address encapsulation. So this is where your multiplexing occurs. So I have to sort of use this to prepare a message. Okay, copy and then I paste here. Then what happens? Okay, source IP, dest IP. Source and destination IP, I'm not going to write the IP addresses here. Then fourth, we will need to encapsulate with Ethernet protocol. Alright, so that means I need my MAC addresses and all. Source MAC, destination MAC. Okay, 1, 2, and 3. And then after that, what happens? Okay, I start to convert it in. I have to convert it into ones and zeros. Okay, voltage signals. Okay, this is actually what we call the physical layer. I have not covered. You'll have to. I just take my word for it. All right, I'll just write some random binary numbers. So this is what happens in the physical layer. You have to convert all of this data into ones and zeros. Okay, so let's say during the course of when you send all these messages out, some of the data gets corrupted. Okay, so maybe the quick brown actually goes through, and lazy dog also gets through. Okay. Unfortunately, this data packet gets that's deleted, okay, or rather gets corrupted. Okay, stuff that happens on the internet. Okay, so after that, what happens? Okay, the quick brown fox jumps over and then okay, I'll just put some garbled message here. Okay. Alright, pardon as a, yeah. So, data corrupted. Okay, so what happens when data is corrupted? That is where your checksum is very important. So, I think I went through checksums before. So, usually what happens when data is corrupted? When data is corrupted, the checksum of the data won't match. Okay, so usually in each of these parts here, under the IP data, IP headers, the Ethernet headers, and of course the port headers, the transport layer header, all of them will have this thing called the checksum, as you can see here. So the checksum is there to, alright, I mean you can convert, okay, the fox jumps over the. Okay, you can convert this using some algorithm, and you can convert it into a number. Okay. However, when you take a look at this corrupted data and you run it through the same algorithm, it will produce a different number. Right? So normally when you have a checksum, okay, the quick brown fox jumped over okay, maybe the checksum is equals to okay, when you run it through your algorithm, you get 451 or something like that, right? And of course, each of these layers also has their own checksum. All right. So I'm just going to so-called all right. I'll just do it for one, right? Okay. I'll just do it for one of these data packets, just to give you an idea of how the thought process goes. Okay, this is the checksum for this part. Okay, this part I'm highlighting. Okay. The transport layer checksum is for this. Let me check here. Okay, pardon me. I think the checksum actually is actually meant for this entire part here. So this checksum, if you run the source port for 8351, destination port 757, along with all the other messages you have there, and then the fox jumps over then you calculate the checksum. Okay, this is 451. Okay, so once this actually, yeah, why not I do it from here? All right, so I'll just do it for the fox jumps over this message, right? I'll say, all right, I take whatever data is here and I calculate the checksum. Checksum is 451. Okay, and then I do IP address encapsulation. Okay, IP address encapsulation, and then it will be here. And then what the IP address encapsulation does is once you fill in all this data, you take this whole thing and you calculate a checksum, right? Checksum 950 or something, I don't know. Okay, yeah. I mean, to be honest, I can't remember if in this layer does this checksum cover this thing, or is it just a datagram? I'm not sure. I can't remember at this point, but I'll just assume it covers everything here. Okay, right. So this source and IP is going to calculate a checksum 950. Then even at the Ethernet frame level, even when you're talking about Ethernet frame, you will also calculate another checksum. Okay, so previously I didn't talk about checksum because we never really cared about data integrity, but now this is important when we talk about sending data from application to application over the internet. Okay, because last time we just talked about data packets as if they're all the same, or we don't really care what's inside. Now we care what's inside because you need to send the right data to the right application. Okay, so over here we'll calculate some other checksum. I don't know why is it 1051 or something like that. Right? Apparently I like the number 51 a lot. I don't know, it's a convenient number. Whatever. Okay, so we'll have all these checksums here. We'll have all these checksums here before we send it to over the internet. Okay, and then we'll have this thing called we'll have a data corruption here. Okay, when the data is corrupted, the checksums, okay, there'll be three levels of checksums. Even when you talk about Ethernet address checksum, right, you will be able to see whether the data inside is corrupted. So what the computer will do, or router, even the router will do, it will look at this checksum. This checksum is 1051, and then it will like examine all the data here, punch it through the algorithm, and then you'll see that the checksum, because there's some extra bits of data here, I don't know what, or maybe some data is missing, it will just look at it, and then it will calculate it. It will have calculated. Yeah, it will have calculated a sum of maybe 1257. Okay, because you have some random extra characters here. Okay, you'll run it through some algorithm. I'm not going to discuss that. Nor am I an expert. But okay, the calculated sum is 1257, and then it'll say, hey, this checksum is different from this calculated sum here. So we can sort of figure out the data is corrupted. So data corrupted, we delete it. Okay, the router or whatever computer may delete the data packet because it's corrupted. Okay, so this is what happens on the internet. Alright, so once the data is corrupted, what happens? Okay, your second packet is like that. Okay, your packet's like that. Right? Alright, after corruption of data, that packet goes missing. Okay, not only that, that packet goes missing, you see this message here, the lazy dog message. The lazy dog message is actually shorter than the quick brown message, right? Okay, the quick brown actually has more data than the lazy dog, so maybe the lazy dog actually happens to travel faster than the quick brown. Okay, the lazy dog actually happens to travel faster than the quick brown. Okay, so after that, after receiving on computer B end, on computer B's end, because I like to use computer B as a receiving end on the second computer. Alright, it will what happens is that the computer B will receive the data like that. The lazy dog will come first, and then the quick brown will come second, because lazy dog it travels faster because there's less data, or for whatever reason it travels faster. Okay, so this is the received message. Okay, this is the received message, and this is the original intended message. Okay, all right. So on computer B's end, this is what happens. Original intended message is the quick brown fox jumps over the lazy dog, and then the received message is called lazy dog the quick brown. What's going on? Okay, but things happen on the internet, and you got to find a way of solving them. Okay, and this is what usually happens with UDP, right? User Datagram Protocol. Okay, here in UDP I don't care about lost packets, right, or the order they come. Okay, you don't really care, right? So this is great if you want to establish very fast connections, but the fidelity of the message may not always be good. So you need to solve these problems. Okay, I need to solve the problems of message fidelity. Okay, especially I need my message to be ordered. Okay, and I also need to know if I have to send data which got lost or corrupted. Okay, so these are two basic needs that you need to have to make sure your message is received in a correct manner. All right, so what do we do? Okay, what do you do? All right, especially this part is important. Especially we need to know if data is corrupted. We need to send the data again. All right, so yeah, how do we do this? Okay, so well, instead of doing things like this, we have to add some steps along the way. Okay, and this is usually what is done for TCP, or Transmission Control Protocol. Okay, TCP, Transmission Control Protocol. Okay, let me see. Yeah, services and segment structure in TCP. This is GeeksforGeeks. You can go and look online again. Yeah, but this is what happens. Instead of just breaking up the message, we'll need to start labeling the segments as well. Okay, so I'm going to type in red. We need to label the segments. Okay, and then let's say this is we have to tell the PC, or tell the computer, this is a segment 1, for example. Segment 1. Okay, so we'll have the whole scenario played out again, but we will put in different what do you call that? A different strategy to combat the loss of data. So we have segment 1, segment 2, and segment 3. Okay, so this is highlighted in a different color. Okay, so all this has to be put into here. All right, segment 2, and then segment 3. And not only that, you should also tell I have 3 segments, and that should be the 4th message at least. Yeah. Okay, I have 3 segments, and that will be either the first or last message, but you have to somehow send this over so that the other guy knows that, yeah, we have 3 segments to look out for. Okay, or maybe the other way to do it, instead of sending it as a separate message, you can say segment 1 or 3, segment 2 or 3, segment 3 or 3. Okay, yeah, I'm just illustrating it here so that you kind of know what's going on. Okay, so it will tell you which segment it is and how many segments to expect. Okay, so let's play through this scenario again. Again, just for argument's sake, let's pretend the checksum is 451. Okay, and then we'll not use the I have 3 segments here, because here it will already say there are 3 segments, right? Okay, so we will do the same thing. Okay, we'll encapsulate the IP address, encapsulate using IP address. The quick brown will be segment 1, the fox jumps over will be segment 2, lazy dog will be segment 3. Okay, just for argument's sake, pretend the checksum is the same. Okay, so this is segment 3, the lazy dog, quick brown fox jumps over the. Okay, this will be segment 2, this will be segment 1. So this is somehow incorporated into the message, or rather instead of doing it here, I rather put the segment number here. Okay, that makes a bit more sense, and that's actually included in your TCP your header. Okay, especially for this TCP protocol. Okay, segment 1 of 3, segment 2 of 3, segment 3 of 3. Okay, so we're going to encapsulate it again. Okay, again the segments are all there. Okay, segment should come before checksum, of course, but I'll just put them here. Okay, lazy dog, the segment should be here. Okay, now let's go through the same data corruption scenario, and somehow this thing is here. Okay, so somehow this connection drops or something. There's some this connection drops. Okay, let's have a segment 1 of 3 here. Okay, somehow this connection drops, the data is corrupted, and then this data packet is deleted. Alright, so instead of you having this scenario, alright, you have on computer B's end, you will have the lazy dog, which is segment 3 of 3, and the quick brown, which is segment 1 of 3. Okay, so after corruption of data, the second piece of data is gone, and then you have the lazy dog coming first, which is well, the computer will know it's segment 3 of 3, and then the quick brown will be segment 1 of 3. Alright, but then at least the computer will know how to switch them around. So the assembled message, instead of the lazy dog quick brown, it'll be the quick brown, and then you have the lazy dog now here. Okay, the quick brown lazy dog. Okay, so here will be 1 of 3, here will be 3 of 3. Okay, then the computer will know what happened to segment 2 of 3. Please send again. Okay, so what happened to segment 2 of 3? Please send again. So it will send the please send again message. You can imagine this happening. It will send the please send again message back to you. Okay, so it will send another request for the fox jumped over segment 2 of 3. So you'll send the message again, then you'll send it over the internet again and again until you get the message. Okay, so quick brown fox jumps over the. Okay, so this is segment 2 of 3 after resending. Okay, so so this is to ensure data fidelity, and then once all the whole message is assembled together, you checked all the checksums, everything sorts out, then you're okay. All right, this is this is part of what happens. This is part of what happens in TCP. Okay, this is a transmission control protocol. Okay, so you need a way of labeling your data with numbers, so that you know how many segments to expect, and then how to assemble your message back together. Okay, and the second thing you need is, of course, you need a way you need a good way of telling the other computer, please send your message again, please send your message again, please send your message again. Especially if you have 10,000 segments and maybe 1,000 of them go missing, you need to send maybe 1,000 messages to request for additional data, you know. So TCP has a lot of back and forth, communication between applications. Okay, TCP has a lot of back and forth communication between the applications because it's please send again, please send again, please send again. All right, so this is like so-called part 1 of UDP and TCP for the transport layer. But the next thing we're going to talk about is how does TCP facilitate this back and forth communication. So I'll not talk about that now. I'll call it a day, but maybe I'll see you next time if I have the time to actually finish up the videos. Thanks for watching.